times to get back to E, to make a full rotation. So you obviously have n rotation operations, because each one's, you're rotating by a different angle, so it's a different rotation. Right? So you will have n rotation operations. I've just said there will be n flip operations, and that's all there are, those two kinds. So the order of this group is just 2n, right? So for D of n in general, we'll have 2 to the n elements, symmetry operations, they're the elements. N of them are rotation type operations, right? And n flips, n flip type operations. Okay, what are the generators? I mean, how do you, well, I've said, how do you go about generating the table? Well, firstly, what is the table? What are the elements? Well, you just generalize. So you just keep going here, like a to the 4th, a to the 5th, a to the 6th, dot, 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 a to the n minus 1. Right? That's your suspicion. Maybe your hypothesis. You're trying to show it's true. And so this would go ba to the 4th, ba to the 5th, dot, 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 ba to the n minus 1. Right? Okay, now each of these a to a power, each of these rotation operations, they're distinct from each other, right? Because if I and j are different, then the angle that you're rotating about is different. So these are quite distinct from each other, right? AI is not equal to AJ if I and j are different, right? Now all these ones, A3, A4, A5, dot, 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 they're all distinct, they're all different from each other. Now, similarly, the B's, the B series, B, BA, BA squared, BA cubed, BA to the 4th, BA to the 5th, dot, 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 BA to the n minus 1. They are also all different from each other. Okay? Now, you can prove that quickly. Assume the opposite. Let's do argument, reduction to absurdity type argument. So assume you have, for different I and j here, assume you have 2 of them that are equal to each other. Okay, left multiply by B inverse, and then you'll get AI equals AJ. But if I and j are different, these are different, so you get a contradiction, right? So these here are all distinct. Now B is a flip operation. So there's no way a flip operation can be equal to any of these rotations, right? Because the rotation, they all stay in the same plane. They stay on one side of they stay in one face, if you like. They don't flip to the other face. So there's no way B can be equal to any of them. There's no way that B can be equal to any of these, right? So So you're talking about, you've got n of these, you've got n of these, they're all distinct. So you end up with 2 to the n different elements. So your dihedral group of n size, d of n, the elements, its symmetry operation elements will be E, A to the 2, dot, 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 A to the n minus 1, and then B, BA squared, dot, 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 BA to the n minus 1. Alright? Now, I can make that sound plausible, or actually prove it, actually, it's more rigorous than that, with a kind of physical, visual argument. And it's quite nifty if you've not seen it before. Now remember, this B here can be any one of n flip operations. So I'll do it for one case, and the other case is actually one of the questions in the problem solving time. So I'll do the other half of it, if you like, in the problem solving sessions probably. Okay, so let's say one of your symmetry operations is what? Say there's 2 here. Right? That's your axis that you're gonna flip around. This one here, 2. That axis there. So now this is quite general. These are, let's say, 5 points of an n-gon, of a polygon of n sides. All right, and I want to show that ABA is B. Go back to this relation. Now, in fact, I'll show that it's the case, but jumping ahead a little, assuming that it is true, your relations for the general dihedral group of n, your relations will be, instead of it being a 4 here, this will be n, right? Because you have to rotate n times to get back to E. When your generator is this, right? I mean, as n gets larger, this rotation then rotates through smaller and smaller angles. Okay? So you have to raise a to the n here to get E. Now B's they're any flip operations. So B squared still is E. Right? So that doesn't change, but this does. That goes a to the 4th. Now this is still the same, interestingly. So I'll now try to show you that's the case. So therefore, the presentation of a dihedral group, Dn, the general case, will be generators A and B. A is this, B is any one of the flip operations, and a to the n equals b squared equals e, and ABA is b. That's the presentation of d of n. Right? All right. Well, let's try to show this. Let's try to show this in the general case when you have n sides. So we're trying to show that ABA is b. Okay. And sort of physically, visually, so it sounds plausible. All right. Say you start here, and you then perform ABA, and you will get the same thing as if you only did B. All right. Now, what is B? B is one of the flip operations. It's flipping. It's about this axis. It's flipping that way, right? Okay. Right. Say we start here, and then we do A. Well, and remember, it's anti-clockwise, right? This is an anti-clockwise rotation. Assume. So we start here, and then we do one A operation. Well, that will take you to here. Make sense? Because you just rotated by one. You've moved this point just one side. So this will go to here because of A. Okay, now you do a B. So this will then flip to here, right? So because of the flip, this will now move here. Okay. And then you do A again. So again an anti-clockwise rotation. So you'll end up here. Make sense? You'll end up here. So I'll say that again. You start here. You apply A, so that will rotate you to this point. Okay? Then you do a flip B, so this will be here. And then you do A again, so it'll take you to here. So you start here and you end up here. But that's the same as just doing one B, right? If you start here and then you just do a single flip B, well, you'll end up here. Okay? Therefore, ABA is the same as B. And that's quite a general argument. I mean, you could have many points. And I've only done 5, but you could have as many as you like, and it's the same argument, the same sort of quasi-physical, visual argument. And so it's true for any n. So this remains true, even for the d of n. Here it was for D of 4, but it's general. The only thing that changes is this number here. As your n changes, you have to have a to the n is e. So one of your relations will change. That's b squared is e, that's the same, that's the same. The only thing that changes is the number here. Alright? Okay, well I've run out of board. In the next session I will talk about subgroups. I talked a little bit about subgroups of D4. What about subgroups of Dn? And that in turn, once I do that, talking a bit about the next session. Once you think you've listed like all possible subgroups of D of n, how do you know you've got them all? So is there some kind of proof that you've got them all? Well, we are one lecture away from one of the most famous proofs in whole of group theory. That's a pretty simple concept. I can just throw it at you and you probably sound very plausible to you. But it's called Lagrange. He's a French mathematician. Lagrange's, well, I'll just spell it, L-A-G-R-A-N-G-E, Lagrange. What does Grange mean in French? Not sure. Grange? Granger? Not sure. I speak French, but I don't know whether, maybe it's just a name. Anyway. So Lagrange's theorem simply says that the size of a subgroup is a factor of the size of the group, its parent group. So, for example, if you had a group whose order, in other words size, number of elements, is a prime number, no subgroups, right? Impossible, because nothing divides a prime number, well, except itself and 1, but you know, they're not, well, let's say no proper subgroups, okay? If you had a group of order 12, then potentially your subgroup might, you have to be careful, it's not always the case, but might have order 3, order 4, order 6. Okay? But you can't have a subgroup of order 5 or 7. Right? Why? Because those orders, the subgroup, well, subset, are not factors. They do not divide into the size or the order of your parent group, your group. Right? So next lecture we will do Lagrange's theorem, which is pretty famous in group theory. Right? So till next session.